Good afternoon, everybody, and thank you for having me here. And I will tell you a bit about ExoMars in two talks. And first of all, I'm a physicist, so bear with me. I'll try to convey to you why this mission is so exciting for the prospect of past life on Mars, and perhaps to possibly tell us something about prebiotic chemistry or environments that may have been important for origin of life that we no longer have access to on Earth. Now, I will start a bit in a strange manner, in the sense that I'll talk first about the landing site, and I'll talk about what the mission is, which instruments it has, etc., in the other talk later today. So let's start from the formation of the terrestrial planets. So, as you know, we owe a great debt of gratitude to the wanderings of Jupiter and Saturn that so generously provided or seeded the inner solar system with volatiles, including water, for example. And the later stages in the formation of the terrestrial planets involved the frequent collisions of a number of planetesimals and later on planetary embryos. All of this to say it was kinetically or a process that liberated a great deal of energy. And in particular, the later stages of the accretion of the planets resulted in what were basically balls of spheres of molten rock. Even after the formation of the terrestrial planets, there would have still been quite a bit of material around falling inward. So if you had been able to walk at that time on the surface of one of these planets, you wouldn't have seen anything because of all the gas and steam liberated. But in essence, you would be walking on molten rock with bits of scum floating here and there. Not exactly a very hospitable place. As the mantle, the process of solidification of the mantle proceeded, then the minerals, the molten minerals, wouldn't have been, as they solidified, wouldn't have been able to keep gases in solution as they did before, and this would have led to the outgassing of the primordial atmospheres, which probably, as is Venus today, were supercritical. They were immense pressure boilers with a lot of CO2, some oxygen, a lot of CO2, nitrogen, and some water. As they started to cool down and crossed the critical point of water, most of the water that was held as steam in the atmosphere precipitated with this phase change and led to the formation of the first oceans, which resulted, and this is probably true for Venus, for Earth. I'm not so sure about Mars, but in the case of Venus and Earth, this resulted likely in planets that were entirely covered by water with no emerged lands. Later on, first volcanic arcs forming islands that these would have been the first emerged lands, and later on the continents started to form, etc., etc. All of this is put together in this little diagram, which tries to summarize the first billion years or so, in this case of Earth. And you see on the top black bar, these phases that I described to you. And at the bottom, we see the formation dates, 4.56 billion years ago, more or less for the terrestrial planets. You see first with the raining down of the oceans, you see this blue area, and later on the appearance of the first subaerial environments, the first emerged lands. The important take-home message of this graph is the blue bar at the top, which on Earth tries to show that from the point when the ocean's temperature became somewhat more clement, let's say below 60 degrees or so, you have this sort of window of opportunity that opens up for the possible appearance of life. And for the case of Earth, conditions on the surface of our planet have been hospitable ever since. Now, in the case of Mars, well, one other important point is that we shouldn't forget is the hydrothermal environment. I mean, initially, and for a long time, the young planets were fueled by energy escaping from the interior. And this would have resulted in much higher levels of volcanic and hydrothermal activity than what we see today. Now, the case for Mars was quite a bit different, because we know that roughly 3.9 to 3.8 billion years ago, Mars had a rather rapid change in its surface conditions. And you see this transition here where relatively quickly, most of the free-running water on the surface of Mars disappeared rather suddenly in terms of geological times. So when you consider the possibility of looking for traces of past life on Mars, this upper blue bar that I mentioned before for Earth is much more restricted. And there's another interesting thing, and that is that because Mars is a much smaller planet, it hasn't undergone the same process of plate tectonics that Earth has. And hence, on Mars, we have access to rocks in a relatively good state of preservation that are much, much older than what we can find on Earth. So there is a real possibility of being able to study terrains with ages in the order of 4 billion years and perhaps older as well. So when looking for potential places to look for signs of life, the question of habitability is important. That is, what is the conditions that render a certain location hospitable to life forms that may have existed at the time? And we think there are such conditions at a number of places on the surface of Mars. Not today, but 4 billion years ago. The other thing that is very, very important, if we're going to have a chance to say anything semi-intelligent about the possibility of life having existed there, is preservation. How do the biosignatures that we hope to be able to study would have made that time travel from 4 billion years ago to today, knowing that they would have, whatever may have been alive there and died, would have been entombed and covered in sediments that could have been potentially, 1,000 meters or more in thickness, that would have been eroded. There are the questions related to survival in terms of exposure to ionizing radiation, aggressive chemical oxidants, etc. Now, when we had to design the mission and look for places to try to find traces of life, there's three things that we could try to do. And I have ordered them in terms of decreasing interest, if you like. We can search in a place where life remains may have collected. Like, for example, let's say at the bottom of an ancient lake that may have received sediments from a large catchment area. The problem with places that only receive detrital biosignatures is that perhaps you may be able to say there was life there, but you will not be able to say much about how it lived or where it lived. The second place, going upwards, is to search in a place that could have hosted life. And this is much more interesting, because if you were to target such a place and found traces of life, you could perhaps say something about how it lived. And the most interesting of all would be to look for life in a place where life could have developed. And there are several advantages to this. Not only you may be able to perhaps investigate the environment where it lived, but conditions for life to appear are in a certain way more restrictive than for life to have flourished. So there are some other advantages, like higher levels of nutrients and perhaps information about possible prebiotic chemistry that perhaps you could have access to in a place like this. So when trying to decide what to look for, there's three main components that we had to consider. First of all, organics are delivered to the terrestrial planets all the time. And these are cosmic organics that have nothing to do with life. The other thing is, in case we would, by chance, come upon something that was still alive, we could perhaps have the opportunity to look for the molecular building blocks of life that you see at the top. But most likely, in the case of past life, we would be dealing with degraded organics. Now, we know that life relies on liquid water, so we had to look for a place where we know today that water existed there for a long time, at the time when the putative life forms would have existed. So we're looking for the remnants or the remains of places that had large bodies and, importantly, low energy water over extended periods. And for reasons that we will see later, it is important that we seek these biosignatures, particularly if we're talking about chemistry, in the subsurface. Now, this is more or less what the mission looks like. It has two elements. We're going to talk more about this in the second talk. There are, let me check the time. Yeah, halfway through. There is a lander that is instrumented, and the goal of the lander is to study geophysics and the atmosphere, but the search for life is with the rover. And you will see that the rover's body is dominated by this black box at the front, and that is a drill. And the take-home message for this part of the talk is that what differentiates this mission for other missions are two things. The drill, which is able to access depths in the order of 2 meters, or it has a maximum reach of 2 meters, and a new analytical laboratory with an instrument to study organic molecules that has a new way of extracting them that is able to bypass the problems of the perchlorates and the oxidants that plagued the findings or the study of organics undertaken by Curiosity. I want to stop a couple of minutes on this diagram. What you see here is simulated exposure of a mixture of amino acids to ionizing radiation. So this was gamma radiation at high doses to try to simulate exposure to 500 million years in blue, 1 billion years in green, 2 billion years in yellow, 3 billion years in red, and 4 billion years in purple. And the point of this is the ionizing radiation that penetrates through the thin atmosphere of Mars and into the subsurface acts as a million little knives that over time slowly cut away at your molecules' functional groups, degrading them beyond our instrument's possibility to recognize them. So when we were talking or thinking about the drill, which is a very complicated piece of equipment, the question was asked, how deep should we go? Now, if we look at amino acids, they're pretty fragile molecules. After cells die and they release the content of their cytoplasm, amino acids degrade very quickly, but they are very interesting. And there are a number of things on Mars that are bad and some that help. One of them is that as you go deep into the subsurface, and don't mean very deep, let's say 50 centimeters, very quickly, the temperature in the subsurface is the average between day and night. So, and it's more or less constant at minus 60 degrees. So the subsurface of Mars is acting like a very nice freezer for us. And you know, amino acids are pretty informative documents as molecules. Now, if we look at, for example, these charts from South Africa that are dated 3.1 billion years, and we look at their organic content, we find that it's very, very low. It's in the order of 0.01%. If for the sake of this discussion, we assume that the 0.01% are entirely amino acids, which I know is not realistic, then for a robust detection with our instruments, we need an abundance in the order of parts per million. So if we start from 10 to the minus 4, we can, let's say, take a hit in terms of distraction of the amino acids that were originally present by a factor of roughly 10 to the minus 2. And if we think that we want to be able to study amino acids that have been there for 4 billion years, we are worried about the purple curve, and in particular, where the purple curve intersects that black line that you see there. And if you do that, you find that you need to penetrate in the subsurface in the order of 1.5 meters. Why do I say 1.5 meters? Because the larger the biomolecule, the bigger the target for ionizing radiation and the faster it degrades. So if we want to be able to study relatively large biomolecules, we need to go deeper. And of course, it will help us a great deal to be able to access places that had been covered by deposits that were denuded later by wind erosion, because then that gives us additional protection. Now, in the mission, we have a metric for trying to prove to ourselves and everybody whether we believe we have found traces of life or not. And a lot of it, the lion's share of it, relies on the chemical biosignatures. If you are interested in learning more about the mission and the 9 instruments in the rover, this is an open document or a special issue of astrobiology with 10 papers. There's one for the mission and one for each one of the instruments. And you can go and have a look. I want to finish the last few minutes by talking a bit about the landing site. So these were the latitudes that we could target. And we were interested in finding very old terrains. We felt that a good mantra for this was the older the better. And you know, the Southern Highlands, which are the oldest, are also very, very high. And these were too high for us to reach with the parachutes. So we concentrated on this area that you see now. And the place that we finally selected after a long landing site selection process is Oxia Planum. And Oxia Planum is in the dichotomy border, and it's at the margins of Chryse Planitia. And it is the mineralogy is dominated by large fields of phyllosilicates. And these phyllosilicates are very finely laminated, and you can think of each one of these strata as the rings on a tree. Each one of them records an instance of sediment deposition and wetting. And in particular, if you compare the stratigraphy of Marth valleys, which is very large, tall stack of clays in the order of 200 meters, what is preserved in Oxia Planum is the very bottom of the stack, so the oldest stratigraphy. In fact, the landing site, the clays are dated at 4.1 billion years. So here you see the arrival landing ellipse. Interestingly enough, if you see on the image that says B at the bottom, there is no limitation to the north towards the northern lowlands. And even though the clays are dated at 4 to 4.1 billion years in age, there is a delta that is dated at 3.9, which you see at the bottom right of the landing ellipse area. This is the delta of the Kogum valleys, which is one of the largest catchment areas in all of Mars. And because this delta is younger than the clays, it means that when it was formed, that area over there was inundated, and we do not see any limit between Oxia Planum and the North Pole. So one of the things that we would like to check at the landing site is the possibility that Oxia may have been the shallow coastal area of what could have been a very large body of water in the northern hemisphere. So here's to give you a bit of a view. What you see here is the landing site is dominated by orange clays, which are the oldest, and blue clays that are somewhat younger. And there is this larger, blacker thing. This is sort of a capping unit of what appears to be some sort of pyroclastic or volcanic material that mantled the entire area and was later cleared away by wind erosion. So this would have provided us with additional protection. In green, you see the landing ellipses. We have two, depending on whether we launch at the beginning or the end of the launch window. And here the pink is good. Pink is the clays, which are our main landing terrain. And here we end by coming back to the previous diagram I showed you at the beginning. And here I put the ages of the deposits and for the landing sites of Curiosity, Perseverance, and Rosalind Franklin. So we are very excited about being able to target squarely this blue area at the top. This landing site is dated at the time when water or liquid water on Mars was really abundant. And of course, geological context is very, very important. We will learn a lot, and is a key aspect of looking for signs of life. If we are lucky, we will land in a place that would have looked 4 billion years ago, like what you see on the left. And if we are less lucky, it will be more like what we see on the right. The challenge for us is that whatever it is that we will find, we will have a mixture of delivered meteoritic organics that will be sort of a signature we have to deal with in the background, and the real possibility for, let's say, chemical traces of life will be mixed with this, and it will be difficult to disentangle it. So I would like to end by summarizing that we think it's interesting to travel back in time some 4 billion years and hopefully explore what may have been the bottom of a Mars ocean or large lake. For the first time, to be able to explore this third dimension in Mars, which is depth, and try to look for traces of life there, and hopefully learn something that may inform future Mars sample return missions. We have put a lot of effort on developing the rover and the drill, and we have high hopes that by looking in the subsurface, we may learn something new and exciting. Thank you so much.